Right, in this video I'm going to go through CC13, and according to the advanced information, the most important part of this topic is group 7, the halogens. Group 1 and group 0 hasn't been crossed out, so you could get asked a 1 or 2 mark question, but it hasn't been highlighted, so it looks like the bulk of the marks on CC13 is going on group 7. In terms of what you need to know for group 7, I've highlighted this table here, which is the physical properties of the group 7 elements. Chlorine, bromine and iodine are the 3 that you need to know. You don't need to know these figures off by heart, but you do need to know the general trend. And the trend is that the melting and boiling points increase as you go down the group. Because they're increasing, I'm going from a gas to a liquid to a solid. If you were asked to explain why, you would say that the intermolecular forces get stronger as you go down the group. Okay, chlorine, Cl2, bromine, Br2, iodine, I2, they are all simple molecules. Because they are simple molecules, there are intermolecular forces. And you can never say intermolecular forces are strong, but you can say that the intermolecular forces get stronger as you move down the group. Therefore, more energy is required to overcome them. Therefore, the melting and boiling points increase. And that's why I'm going from a gas to a liquid to a solid. You also need to know the color. And again, in terms of color, you can see that we're getting darker going down the group, from green to brown to purple black. Iodine, be mindful of iodine. It can be described as purple, black. You might even see it being described as grey. Okay, the biggest indicator they're talking about iodine is the fact that it's a solid, but it can be described as purple, black or grey at room temperature. As well as physical properties, you'll have to be able to describe the chemical properties. And again, you need to know the trend. So unlike the alkali metals, the halogens get less reactive as you move down the group, and you need to be able to explain why. So I've drawn out chlorine, bromine and iodine here, and you can see as you move down the group, they get bigger. The halogens are all trying to gain 1 electron into their outer shell. Iodine finds this the hardest to do, because there are so many shells separating the outer shell from the positive nucleus. That negative electron that you're trying to gain is attracted to iodine because it's attracted to the positive charge in the nucleus. If you've got all of these electron shells in the way, it's much harder for that outer shell electron to become attracted to the nucleus. Compare that to chlorine. You're trying to attract this outer shell electron. I mean, the nucleus is right there. So there's less electrons, shells in the way. There's a stronger attraction between the nucleus and the outer shell electron that you're trying to gain. In terms of how you would actually phrase that in an exam, I've written it out here in your worked example. Everything that I've underlined has to be included. Specifically, take note of the words outer shell. You can't just say it wants to gain an electron. You have to say into the outer shell. And again, here, when you're talking about the attraction with the nucleus, it has to be to the outer electron. You have to specify the word outer. The other thing they can ask you, and this is a potential 6-mark question, is they'll ask you, well, prove it. Okay, you know that the halogens are getting less reactive as you move down the group. Describe an experiment that proves that. And underneath here, I've written out an answer in words, but what they may ask you for is equations. And in the answer I've written in the book, in your booklet, there are no equations. I'm just going to redo this one, including equations. So when you're doing this, it's chlorine, bromine and iodine that they want you to consider. And as you move down the group from chlorine to bromine to iodine, they should be getting less reactive, but you need to describe an experiment that proves that. So what I'm going to do is I'm going to start with the most reactive one, that's chlorine. Chlorine, as an element, is diatomic, so I'm going to write it as Cl2. And then I'm going to react chlorine with a compound that contains bromine. Now, you can pick any compound, but I would advise you to pick a group 1 metal compound because the formula is easy to write. So I'm going to pick sodium. You could pick lithium, you could pick potassium. I'm going to pick sodium because when I write the formula of sodium bromide, it's just NaBr. +1 on sodium, -1 on bromine, the charges cancel, and the formula is simple to write. So I've got chlorine as an element by itself, and I've got bromine in a compound. And the rule is, if the halogen by itself is more reactive than the halogen in the compound, they will swap places. I know chlorine is more reactive than bromine, so I know that they will end up swapping places. And when they do, sodium is going to become bonded to chlorine. Sodium is going to become bonded to chlorine instead of bromine, and bromine will be left by itself. So you'll note here, when I'm writing the halogens by themselves, they are diatomic. When they're elements, they are diatomic. And when they're in the compound with the group 1 metal, because it's +1, -1, the charges just immediately cancel. And that's my equation. At the moment, it's not balanced. I've got 2 chlorines on the left. I need a big 2 to give me 2 chlorines on the right. I've got 2 bromines on the right. I need a big 2 to give me 2 bromines on the left. And then my sodiums are also balanced. So that would be my equation for the reaction. I can then take chlorine and do exactly the same thing, but with a compound that contains iodine. So I'm going to stick with sodium. Formula of sodium iodide is NaI. Because chlorine is more reactive than iodine, that will swap. I'm going to get I'll get NaCl, and I'll get I2 left by itself. This again shows me that chlorine is more reactive than iodine, hence it takes its place, and to balance it, it's exactly the same as balancing it above. So I've shown that chlorine is more reactive than bromine, I've shown that chlorine is more reactive than iodine. I now need to do bromine and iodine. So I'm going to take bromine by itself, it's Br2. I'm going to react it with a compound that contains iodine. Because bromine is more reactive than iodine, they will swap places. I'm going to get sodium bromide, I'm going to get iodine by itself, and then I will balance it. So that would be my 3 equations. Now, if it doesn't specify equations, you could write it in words. If you know that you don't really like writing simple equations, just write it in words. You'd write chlorine plus sodium bromide goes to sodium chloride plus bromine. You can absolutely write it in words. If you are going to write simple equations, make sure you can write these equations and make sure you can balance them. So these are the 3 reactions that are going to take place. But in order to get the full 6 marks, you need to describe how you know that these reactions are taking place. And for each one, you're going to have a color change. Now, if I scroll back up here, to this, all right, we've already looked at the colors of chlorine, bromine, and iodine, green, brown, and purple. But when you're doing these reactions, it takes place in solution. So you dissolve these elements in water, you dissolve all the compounds in water. And when you dissolve them in water, the color is going to fade. So chlorine is going to go from green, it's going to look colorless, dissolved in water. Bromine, instead of looking brown, is going to look orange, dissolved in water. And iodine, instead of looking like that purple black solid dissolved in water, it looks brown. And all of these reactions take place in solution. And the rule is that the halogen by itself determines the color. So when I've got chlorine by itself on the left-hand side, that dictates the color, and chlorine in solution is colorless. On the other side of the equation, I've got bromine by itself, and bromine in solution is orange. So the reason I know this reaction takes place is because I see a color change from colorless to orange. Down here, again, I'm starting off with chlorine, which is colorless. On the other side, I've got iodine, and iodine in solution is brown. So I'm going from colorless to brown. That's how I know it's taking place. And the last one, I'm starting off with bromine, which is orange in solution, and it's going brown because I've got iodine by itself on the right-hand side. So as well as being able to write these equations, you also need to be able to give me the color change. You have to tell me how you know the reaction is taking place. What do you see? That is it's quite likely that could come up as a 6-mark question. If not as a 6-mark question, they could ask you it as an individual question. Write one of these equations for 3 marks. They could ask you a bit of color change for a mark. The other thing that they can ask you to do, they might not, because on paper 1 they've already asked you to prove that something is a redox reaction, but we will go through it anyway. They can give you these reactions, they're called displacement reactions, and they can ask you to write an ionic equation for the displacement reaction, and then to use the ionic equation to show what's being oxidized and what's being reduced. So first thing I'm going to do is I'm going to write my ionic equation, and to do this I'm just going to quickly run through each one to see if I've got something ionic or if I've got something ionic or if I've got something covalent. So Cl2, that is covalent. Sodium bromide, a metal and a non-metal, that is ionic. Sodium chloride, metal, non-metal, that's ionic. And then bromine, 2 non-metals, that's going to be covalent. When I'm writing an ionic equation, if something's covalent, it's just going to stay exactly the same. It doesn't contain ions, so Cl2 is going to stay as Cl2. The exception to that rule is if you've got an acid, but Cl2 by itself is not an acid, so I'm just going to keep it as Cl2. Then I get on to sodium bromide. This is ionic, and when I'm writing an ionic equation, I need to show the ions it contains. So it contains sodium. Sodium is in group 1. It's got a +1 charge. It's got a bromide ion. Bromine is in group 7, so it's got a -1 charge. And that big 2 at the front tells me I've got 2 sodiums and I've got 2 bromines. That 2 affects the sodium and it affects the bromine. On the other side, I've got another ionic compound. Again, I've got sodium. Sodium's in group 1. It's got a +1 charge. And I've got chlorine in group 7 with a -1 charge. Again, there's a big 2, which means I've got 2 sodiums and 2 chloride ions. And then at the end of the equation, I've got Br2. Br2 is covalent. It doesn't contain ions, so I don't change it, and I write it the same way underneath. Next thing I do is I cross out what we call the spectator ions, the things that are exactly the same on each side. And what I'm left with is my ionic equation. So Cl2 plus 2Br minus goes to 2Cl minus and Br2. And you can write that out again underneath, and that's your ionic equation. If you're asked to do that, that will be worth 3 marks. And it doesn't matter which of these equations I use, you follow the same process each time. They can then ask you for another 4 marks to use this ionic equation to describe what's being oxidized and what's being reduced. So we're going to start off by looking at chlorine, and we're going to see what happens to chlorine as I go from the left hand side to the right hand side. On the left hand side, chlorine is an element. When it's got an element, it has got no charge whatsoever. So I'm going to draw a little 0 underneath. Oh, my pen is a crap. A 0 underneath because it's got no charge. On the right hand side, chlorine does have a charge. It's got a -1 charge. So what's happening to chlorine if it's going from no charge to having a -1 charge? Well, -1 in terms of electrons means it has gained electrons. And if it's gaining electrons, then chlorine has been reduced. So I'm going to write down here, chlorine gains electrons. Therefore, chlorine is reduced. Technically what's happening is 2 chlorine atoms each gain 1 electron to form 2 chloride ions. That would be the most technically correct way to describe it. But if you try and write that, you're kind of in danger of misusing the words atoms and ions, and it's not required on the mark scheme. You can just say chlorine gains electrons, so chlorine is reduced. Now we need to look at bromine, which is also changing. So it's starting off with a -1 charge. You can see it there in my ionic equation, and it ends up as an element with no charge at all. And this is where you do need to be mindful, okay? So it's going from -1, it means it had gained an electron, to neutral. So the electron that it had gained, it's obviously lost, so it's losing an electron. But when you're describing what is losing an electron, you need to be mindful that you've got an ion, okay? So I have to say that the bromide ion loses an electron. So the bromide ion, which you could also just write as Br minus, is oxidized. And they will penalize you if you say bromine loses an electron. You have to specify that you've got the bromide ion, either by writing bromide ion or writing Br minus. There's loads of examples of these types of questions in the booklet, and you've got the answers. So if you need to, go and practice writing these equations for displacement reactions, turning them into ionic equations, and then using them to work out what's oxidized and reduced, because they've highlighted this as a key area. You know, potentially you might get a 6-mark question on it.